Welcome once again to tutorial on the Karnaugh map. Okay, so in this video I'm going to teach you how to simplify a Boolean function using a 3-variable Karnaugh map. Okay, so we're basically going to use a 3-variable Karnaugh map. Okay, or rather a 3-variable K-map in short. Alright, so let's take up a problem statement over here. Let's say we have a function that's given by f equals sigma, okay, small m, and the numbers inside the bracket would be 0, 2, and then 3, 4, 5, and 6. Well, as I explained in the previous tutorials that, well, these numbers that you can see over here, they actually represent the cell numbers of of the various cells that are present on the Karnaugh map. Okay, so now over here we can basically see now the problem statement that we have in order to illustrate the example. It says reduce the function f, okay, that's just given over here, with a K-map and implement the reduced expression in NAND logic. Okay, so here we can see, if we just take a good look at the function that's just given over here, this one, okay, we can see that the highest cell number in within the brackets is basically 6. So in order to accommodate this particular function within a K-map, it's quite obvious that we would require a maximum of 8 cells, okay, that needs to be present in a K-map. So we'll be needing an 8-celled K-map. Okay, so an 8-celled K-map would obviously be 2 by 4 K-map. Okay, so that should consist of 8 cells basically. So now if we're dealing with 8-celled K-map, okay, then it's quite obvious that the number of variables is 3, because as I said, the maximum capacity of a K-map is given by 2 to the power n, where n is obviously the number of variables present in the the function, in the Boolean function that needs to be reduced using the K-map. Okay, so here we have it as equal to 2 to the power 3, since we have 3 variables, so that gives us 8. So since we required an 8-celled K-map, that means that our expression, which we shall basically reduce using the K-map, will have 3 variables. Okay, now let's just take the variables as a, b, and c for our just for our convenience. Okay, so now if I just go to solving the problem using the K-map, then let's just draw a 8-celled K-map first. So it'll just be somewhat rectangular in shape. Okay, so there you go, that's a rectangle. And let's just put the variable a for the rows. Okay, so this K-map would obviously have 2 rows and 4 columns, because that's just the convention. So there you go, that's 1, and then 2, and there you go, 3 and 4. Okay, so for the rows we'll have basically 2 values for the rows of the binary numbers, that's 0 and 1. And on the other hand, for the columns, we'll have double-digit binary numbers. Okay, so it'll be something like 0, 0, and then you'll have this one as 0, 1, and then again 1, 0, and 1, 1. Much like the examples that I previously shown you in the earlier tutorials. So we'll have basically we'll need 2 variables to designate such values of binary numbers. So we'll just keep the variables b and c for the designation of the columns. Okay. So now let's just what remains is the number of the cells. So let's just put it over there. So we got the cell number 0, 1, and then 2. Sorry, there. This one would be 2 would be here, and this will 3. Okay, and then we got 4, 5, and then 6 and 7. So kindly don't make the mistake that I was just making a little while ago. Okay, so you should always make the 3-variable Karnaugh map something in this way. Okay. Okay, so now it's just the time where we just filled it up with the necessary, fill up the cells with the necessary values. So if we just take a look back at the expression over here, then we can see that here we have a sigma term present in the expression. I mean, that's the basically the Boolean function that's being assigned, or rather to be reduced over here. Okay, so now the sigma sign, as I said earlier, it basically denotes that the Boolean function is an SOP type function, which means it's a sum of products. Now over here, any sort of complementary quantity is obviously represented with the value of 0. So here 0 represents a complementary quantity, while 1 represents a non-complementary quantity. Okay, and of course, whenever we're working with a SOP type function, then whichever cell numbers are present in the functions, we are supposed to put a 1 over there. So if we just go for the problem, or rather go for the function over here, then we can see that the cell numbers 0, 2, 3 are present in it. So we'll just put 1s in the cells 0, 2, and 3. And then again, we have the cell numbers 4, 5, and 6. So 4, 5, and there you go, 6. Okay, so now we've just finished filling up our K-map. Okay, now what remains is the grouping of the necessary cells that are just assigned the values to. Okay, so we can see that all right, so we can just see if we just as I said earlier, that you can always fold a Karnaugh map sideways. Okay, so if you just care to imagine that you're folding the Karnaugh map sideways, just as if it were a piece of, or rather a sheet of paper, okay, then if you just try and fold that sideways, then you'll obviously find that the cells 0, 4, and then 2 and 6 will just come to be, they'll just come side by side as adjacent cells, and they'll just form a quad. Okay, just try and imagine it something like that. Okay, much like you're folding a piece of paper. So it'll just you'll basically discover that the cells 0, 4, 2, and 6 forming a quad, as they will just appear to be coming adjacent to each other. Okay, so with that kept in mind, okay, we can just group up the cells 0, 4. Okay, on one hand. Okay, I'll just use a different color over here. Okay, we can just group up the cells 1, 4, and then you got 2 and 6 together to form a quad. Okay, now on the other hand, we have the cells 3 and 5 that just remains. Okay, they won't be alone because we'll have the cells, I'll choose a different color in this case. Okay, we'll have the cells 2 and 3 grouping up together. All right, and then again we'll have okay, I'll just take green, and then we'll have the cells 4 and 5 also grouping up together to form a pair. So we have the cells 2 and 3 on one hand, and on the other we have the cells 4 and 5 forming forming pairs basically. Okay, so we got 2 pairs and 1 quad. All right, so now it's just the time to basically simplify the functions as much as possible. So let's just take the pair, that's the blue pair, as the group number 1. Okay, so I'll just use the blue ink over here. So this is group 1. Okay, I'll just call it G1. So for G1, the necessary expressions with 3 variables, the necessary SOP expressions would be given as something like, as I'm just going to write down over here. So we have over here, we can see that the value of the form of the expression for cell number 3 would be something like, you can see that the value of the first variable, let's say row variable, is 0. So since A is a row variable over here, it'll have a complementary sign over it, while the values of the column variables, that's B and C, are both 1s. So which means that B and C both would be non-complementary variables, right, for the cell number 3. So we'll have the the Boolean expression designation for the cells would be something like A bar B C. Okay, so that's the expression for cell number 3. And also we have a cell number 2 in the group also, so we can just basically, since this is a SOP type of K-map reduction system, so that's why we are basically will be arranging all the expressions that we're going to get over here in the form of SOP functions. Okay, so for group number 2, we can see that, well, the row value that's of course A is also 0, so we'll have another A bar right over here, while we can see that the value of the column variables is B and C. We can see that B is a non-complementary quantity over here because it has the value 1, while C would, since it has the value 0, would again be a complementary quantity. So for the cell number 2, the expression would appear something like A bar B C bar. Okay, there you go. Alright, so that's for the cells 2 and 3. That's group 1. And now let's see if we can basically reduce it to something something more. Okay, so let's see. We have here, as you can see, A bar B common for both the terms. I mean for both the min terms. Okay, so we're just taking A bar B out, and whatever remains inside the bracket would just basically get reduced to 1 and get multiplied with A bar B, giving the same value. That's just obtained by the basic laws of Boolean algebra. Okay, so there you go. That's the reduced expression for group 1. Okay, so let's just go to the other group. That's the green pair, okay, formed by the cells 4 and 5. So we're going for group 2 over here. Okay, so for group 2 we have the cells 4 and 5. Now we can see that the value of the row element, that's A over here, is of course has a value 1, so which means that it's a non-complementary quantity. And on the other hand, okay, for cell number 4 we have both the column variables to be complementary quantities since they have 0 values over here. So we're gonna write it down as B bar C bar. Okay, so the entire expression becomes A B bar C bar. Okay, and then plus we're going to add it up with the value of the min term for group for the cell 5. Okay, so we again have A to be the non-complementary value. Okay, and of course we, in this case, for that of cell 5, we have B as the 0 and C as a 1. So we're just going to write it down as B bar C. Okay, let's see what we have common from here. Now if we just examine the min terms closely, we can see that we have A B bar as common in both the terms. Okay, so we're just going to take A B bar out, and whatever remains within inside, okay, that is just again reduced to 1, and that being multiplied with A B bar is going to yield the same result. Okay, so this is reduced by the basic laws of Boolean algebra once again. So we're just not elaborating the process over here, as it'll just take more time. So okay, now what remains over here is the quad group over here concerning cells containing cells 0, 4, 2 and 6. Okay, so we're gonna go for the quad right now, so that's gonna be our group 3. Okay, so here we can see that we have the cell number 0 first. So for the cell number 0, the min term would obviously be, we can see that both, all the 3 variables, that's A, B, and C, all of them are 0 for cell number 0. Okay, so the min term for cell number 0 would obviously be A bar, B bar, C bar. Okay, and then we also have the cell number 2 over here. So for cell number 2, the min terms would be, as you can see over here, for cell number 2, the variables A and C are zeros. So A and C would be complementary variables, whereas only B has the value 1. So the min term would be A bar B C bar. Okay, that's for cell number 2. And then for cell number 4, we have, for both cell numbers 4 and 6, we'll have the row variable, that's A, to be a non-complementary value. So since it has the value 1 over here. Okay, so on the other hand, for cell number 4, we have A as the non-complementary variable, whereas B and C are complemented. So they go to be B bar C bar once again. And finally, for cell number 6, the min term appears to be something like, okay, A B C bar. Let's just check it out. Okay, that's perfect. So there we go. Now from all the 4 min terms that we've got here, if we just try and reduce them once again, we can just, if we just take them in pairs. Let's just take the first 2. Okay, so we see here we have the terms A bar C bar common for from the first and the second min terms. Okay, so we just take them out, A bar, C bar, and the rest that that's just reduced to 1 by laws of Boolean algebra. And then for again we do the same for the second two minterms also. And from over here we find that we have the the variables A, C bar as common. Okay, so we're just extracting A, C bar, and the rest is just reduced to 1 again by Boolean algebra laws. And finally over here we have C bar common, so we're just finally extracting C bar out, and whatever remains, that's A bar plus A, is just equal to 1 again by the same laws of Boolean algebra. Okay, so finally we got A bar B, AB bar, and C bar as the reduced results. So the final expression, that's the reduced expression, is gonna be something is gonna be written as something like F min, and that would be equal to A bar B plus that of AB bar plus that of C bar. So this is exactly the result which we are going to obtain by just reducing this expression, this particular function, SOP function, using a 3-variable K-map. Okay, and now if you just look once again in the problem statement, we shall see that it's been asked to reduce the expression in NAND logic. Okay, so we're going to construct the circuit diagram over here. So now if you just take a look at this reduced expression over here, and then just try and reconstruct this again using NAND logic, then the whole thing appears to be a NANDed term. So we're just going to write this down over here, and okay, so let's just first write it down. Okay, there you go. And if you're just thinking of how to convert this into NAND logic, then I'll just tell you to just put 2 bar signs over each of the minterms. So we got 2 bar signs over this one, the second, and here the third. Okay, so now if you just apply De Morgan's laws. Okay, so now De Morgan's laws basically state that if this is what we have, okay, that this can be written again in a different way. So it can be basically written in something as I'm just writing down over here, in somewhat this type of form. Okay, where each of the minterms now gets multiplied with each other. Okay, so there we go. And finally this is going to be C. Okay, so this is the result in NAND logic. Okay, so this is the exact the type of result that we require in NAND logic. So this is the NAND logic which we desire for our circuit construction. So we'll just go forward and construct the circuit diagram over here using the same. So we have 1 NAND gate. Okay, so we're gonna need 3 NAND gates in total. Okay, there you go. We have 2 NAND gates over here. So there you go. Okay, and so if we have A bar and B for 1, okay, so that we have A bar B complement, and for the next one we'll have A and B bar, so that we have AB bar complement as its output. Okay, and finally we have the term C that's being fed into as the input to the third and final NAND gate once again. So here it'll just be a 3 input NAND gate that we're basically using over here, and finally the output, as you'll have over here, would be nothing but this result F min. So we're just going to write here F min. So that's exactly the result which we are getting as the output. Okay, so that's the circuit which you're gonna basically be deriving for this particular function over here. That's the reduced function over here. Okay, so finally we're just wrapping up our our discussion right at this point, and hope you've just understood how to reduce an expression using a 3-variable K-map. So it's just gonna be a short goodbye from here right now, and just keep watching.